Hi, everyone. Hello, welcome. My name's Allison. I'm an FE PhD student. It's an honor today to introduce Andrew Goodman-Bacon. He's a senior economist at the Opportunity and Inclusive Growth Institute at the Federal Reserve Bank of Minneapolis. He works on applied topics about the history of American health and safety net programs such as Medicaid and income support policies, and on methodological topics and differences. He's a McAllister graduate, has a PhD from the University of Michigan, and is also an adjunct professor teaching econometrics at the University of Minnesota. His talk today is on new developments in differences, and I forgot the most important thing. We have a very cool country. Andrew Goodman-Bacon.
Okay, thanks. Well, I'm really glad to be here, and there's like many seminars worth of things to say about this, so I want to make sure I get to sort of one natural stopping point in what I say today. But as always, I have to just assure you that nothing I say about diff and diff is what the Federal Reserve System believes about differences. So I'm going to jump into it because, and I'll preface like the way that I'm going to structure this by saying a lot has been happening methodologically in how we should conceive of and interpret and estimate differences analyses, especially kind of more complicated ones. And I think what we're learning, the overarching theme that we're learning about when you say I've got a big complicated diff and diff, is that actually it is made up in some sense of simple diff and diffs. And so instead of taking the methods into a space where you say, well, this complicated thing is even more complicated and fancy, what's actually happening is that we're breaking those seemingly complicated analyses down into simple components, which I love. I think that's great. That's kind of all that I really understand. And the way that you can conceive of and keep your thoughts straight about how this kind of breaking down process works is to approach these analyses kind of in the right order. And I'm going to just tell you in this talk like what I think is the right order. And specifically, I'll talk about like a staggered timing one, where you're studying some intervention or policy that starts at different times for different units. But I will emphasize too, everything that I'm going to say also applies if you're studying a different kind of quote unquote complicated diff and diff. Like, what if you're studying a treatment that's not on or off? It has multiple levels or variation in treatment intensity. All the sort of intellectual steps apply, and they'll get you down to a good estimation tools and proper interpretation in the same way that is happened. So I'm going to label this sort of like a blueprint, and I think of it like a series of questions. And I want to emphasize, like, I'm an economist, and so maybe I'll say, here's how you should do this, and you'll say, yeah, duh, we all already do this in epidemiology. But I'm laying it out this way because this is not how most economists who've been using differences for the last 30 or 40 years have done it. And I'll highlight what I think they have done and where it led us wrong. So to me, the thing that now I believe after talking to econometricians for 5 straight years, so the very first thing that you need to do is just ask, like, what do you even want to know from an analysis? And that can have many different answers. I am a person who used to write papers, and I would say, I would like to estimate the causal effect of something. And that is a phrase that I will no longer write in a paper ever. Because when we can be more detailed about what causality means and what different causal parameters mean, that doesn't really have a lot of content. The causal effect doesn't tell me anything. And that might sound kind of pedantic, but what I've learned in working in this area is that the way that you define what you want to know immediately shapes which path you'll take through your analysis, how you're going to handle your data, how you're going to handle covariates, what estimation techniques you're going to choose. And so getting it right at the top really matters and will really keep you from going down like wrong paths in terms of what you do and in terms of how you interpret the number you get at the end of your paper. And also emphasize, this is not really even a diff specific thing to do. You should do this in any possible study. Then we're not even going to jump to data. Then you have to say, well, if I want to know that thing, and that thing is well defined in some sense, you're never just going to get to know it. You're going to have to make some kind of assumptions in order to figure it out. And before you jump, again, like something that a practice that I inherited when I started doing empirical work was to go into the data and just check if something is there, see like, is there going to be a result here or not? And then judge whether, papers were worth writing or projects were worth pursuing based on that. And I might not have been completely cured of that habit, but I don't think that it's the right way to go because, suppose that you thought there was some good reason why your paper was going to quote unquote work, but you hadn't really reckoned with plausibility of what you were going to have to believe in order to like run with that interpretation. Well, then you're kind of screwed on the back end because you're like, I have a number that looks good, but it's based on untenable assumptions. So understanding what you have to believe here is really important. And that's now moving from this world of defining like, what do you want to know to what are the tools of econometrics and statistics going to allow you to do. Different, again, this question is not definitive specific. Sometimes if you're lucky enough to do an RCT, this is pretty easy. You don't have to believe very much because you control so much on the front end. But different methods are gonna answer this question differently. And then, like I was mentioning before, they will lead you to doing different stuff with the data. So diffindiff, for example, today, like the thing you're gonna need to believe in order for a diffindiff analysis to be a good idea is some kind of a parallel trends assumption, which we will be a lot more specific about too. But if you were gonna do an instrumental variables type analysis, you would need to believe exogeneity or an excludability. You need independence assumptions. There's all sorts of different statistics words, and like this is where they enter in this analysis. And then once you have those two things, then you can actually figure out what is a good estimation approach. And this is where I want to emphasize that I think practice really diverged from this process before. Much more typical, I think, way to do diffindiff analyses in practice was to say, what regression should I run? Which is a question I've asked myself many times. But regression is an estimator. That's jumping way down the chain. And it's saying like, let's just start here and I'm going to choose a tool that I would like to use. And then I'll figure out what it does later. It's like saying, I made you a very delicious dinner. And why is it delicious? Because I used a knife. Okay, but that's not a sensible thing to say. This is, and then, you can go from 1 and 2 down to this third step. Like that's where you need some math. That's where you need to understand something about the structure of potential outcomes and assumptions and statistics, but it's going to not lead you astray. It's going to settle on a good choice of how to handle the data and avoid a lot of problems, which I hope we can talk about. I won't talk anything about here. I think it's also a very good idea to push on the plausibility of your assumptions and think about robustness checks or sensitivity analyses. We won't talk about that. And then, of course, at the end, you get a number. And presumably it's a number that you think is pretty believable, and that's great. And then you get to interpret it and your paper's done. So for diffindiff specifically, I touched on this a little. This set of questions is not different if you have a continuous design or a staggered design or even a simple design. If you want to incorporate covariates, these are all the same questions that you want to ask, and we'll come back to this as well. So I want to start by just walking through these questions. And my favorite slide deck on this would have worked really well because actually the simplest diffindiff methods were developed by epidemiologists. I would have loved to talk. I mean, I would have wasted my entire seminar time talking to you about John Snow, or my favorite person is Ignaz Semmelweis and puerperal fever. But instead, I'm going to talk to you about a more recent example. There was this really nice recent JAMA Health Forum paper by some researchers at Humana studying the effect of bundle payment reform on how much it costs people to get like hip and knee replacements. And this is, it's a really important question. This is something about how much these operations cost. And, we don't know a whole lot about how these bundle payment programs work for Medicare Advantage recipients. So that's like many people in Medicare now get these private plans. So it's a pretty well-defined, like I think practical health policy question. Can we change the way we pay for stuff and make that stuff cost less? So let's think about that question from the very first step here. And just in general, the defining of the parameters that's actually the most important thing that I've learned to change about how I approach this, because I used to be kind of vague about it, but it's really important to know where these things can come from. And even without getting specifics, I think we can appreciate that there's a real push and pull when you start your study off and you're like, well, what parameter do I want? So some of that is about want. Some of it's like saying, you want to know, what did this bundle payment program do? Sometimes you might have a theoretical kind of model of some process, and you say, well, this parameter of that model is really important. That is a parameter that I want to know. And that's all kind of guiding what would be an interesting thing. So in economics, there's a lot of this model parameter motivation for things. Sometimes it might just be a certain kind of treatment effect that you haven't observed before, or you haven't estimated before. But there's sort of a want side, right? But there's also like limitations on what you can even target. I mean, I can just say that I want any type of causal effect I want, but it doesn't mean I can get it. So you kind of have to get your hands dirty in this whole process of the design phase of these studies, so that you know, like, okay, well, I might love to know the entire distribution of causal effects, but that's really hard to know. So maybe I'm not even going to say that I want it because I know I can't get it. So you have to kind of understand how the assumptions work. So it's really important to know. I mean, and then also the thing I'm noting here is your data is going to limit you too. So I kind of love this as a first step because it shows you exactly where the value of better or different data comes. If I have microdata on something instead of aggregated data, I can all of a sudden, I can ask for different types of questions. I can ask for treatment effects for subgroups. I can look at distributional things. And so I might have always wanted that, but the data allow me to do it. So to me, I like knowing like where each new development fits in and make my analysis better. So just knowing the difference between, what in theory is something that you can want, or it's going to be challenging to get, so you don't want it, versus what are the data you're dealing with and what are they going to allow you to do or keep you from doing. So now we got to get a little more detailed. So I'm going to, because we're going to be talking about staggered timing, I'm going to show you some potential outcomes notation. But that might seem slightly more complicated than you're used to. Like normally these are Y1 is the outcome under treatment and Y0 is the outcome under the control condition. But I'm going to use slightly different notation. We're going to say that there's a treatment that turns on at a time called capital G. And this is going to help us when we move to a staggered timing case. Right now, just think about a situation where there's just a treatment and no treatment. And we're just going to call treatment outcomes Y of G. And we're going to call control outcomes, potential outcomes, Y of infinity. Now that's like econometrician is like infinity. The reason I'm having it be infinity and not zero is because when we think about something that's rolling out over time, something that never happens like at time infinity. So if you're untreated in that sense, it's like your treatment never occurs. So that's why we're using infinity now. But let's just stick with it for the simple case. So I also want to note that there's some assumptions that are already embedded in writing it down this way. Nobody else's outcomes are in that notation. So we have this stable unit treatment value assumption, no spillovers. And the way I kind of wrote the thing in brackets suggests that before your treatment turns on, this is assuming there's sort of no anticipatory behavior, so that we really do see your outcome in a sort of untreated state of the world if your treatment hasn't begun yet. But with this, we can just define like individual level causal effects. So for one unit I at one time period T, their causal effect of this for that person or that unit or that firm or whatever is just Y of G minus Y of infinity. And that's going to be the obviously in this situation, like the very basic component that we use to define causal parameters. It's not restricted in any way. This is like the beauty of doing a kind of causal inference approach rather than like something that comes from a more fully specified model at the outset. So let's go back. So we got that in mind. Let's go back to this paper. What do they say is their objective? They want to evaluate whether a voluntary bundle payment program was associated with changes. I'm going to highlight this and say they were very, very careful in the paper to say associated everywhere. That's very good. But this is to talk about causal inference, so I'm just going to replace it with the word caused. So pretend that that might not be their objective, but this is our objective to talk about whether this caused anything. And so now we're at a point where we need to put our foot down a little more firmly on what is the parameter that we are after. So not just something vague, but now we're going to use the notation to define the object that we want. And it's just true that most diff and diff analyses target an average treatment effect on the treated. In terms of these things, if you had an RCT, you would be targeting the average treatment effect among everybody. But for diff and diff, it doesn't work that way. I'm not trying to make you think that you should know that like right off the bat. That comes from just like seeing how diff and diff works and what assumptions you need. You could make other assumptions and target something different, but this is just what we're going to be after. So it's the, as we know, it's the average, which you can see by the expectation causal effect, which you can see by the individual causal effect inside, but it's only averaged over the units that are treated at time G, or treated in this. And what I want to note, and I think I'll probably try to highlight this with this hideous pink color throughout the talk, wanting this is a choice. you could, again, you could choose to want other things. You could want an eight, you could want an average treatment effect. You would either need stronger assumptions or a different design. You could want to know something about the distribution rather than just the average of that effect. That is perfect. That's a really important thing to want sometimes, but you're going to need other data. You're going to need other assumptions. And you might want to know something about how this effect changes, not just at one time period t, but at t+1 and t+2 and t+3. Super interesting, but you have to observe that stuff in your data. So you choose what the answer is here, and it's a little bit of a constrained choice, but you choose. And then, of course, that's not a thing that can be calculated because it contains a piece that's not observed. What would the average outcomes under the control condition for the treatment people? So that's what we got figured. So let's imagine, I'm going to start off in a simplest world where the parameters we're after are quote unquote the ATT. And I will just like foreshadow that when we move to a more complex design, there is not the ATT anymore. There's many, many ATTs. And we will think about simple ways to get each of them and then aggregate them up at the end. But here there's like one. And we're going to do it with a 2x2 differential. So these are data that I just pulled off of like a figure from their paper. I don't have their special humana data. I just saw their main picture. And so let's imagine that the world consisted of physician practices that adopted this bundled payment program in 2017, and then physician practices that did not do that. And that our data consisted of spending for these knee and hip replacements in 2016, so prior to the adoption, and then also another observation in 2018. So this is data. These four dots are the data points. Parallel trends in words, we're just going to need to assume that untreated potential outcomes or the treated units would have changed in the same way that the actual untreated outcomes did for the controls. And in math, it's just saying we are going to assume that you can't see my thing. I never remember if I can get a little marker. Oh, here we go. There we go. So it's going to assume that the change in untreated outcomes for treated units, this is the piece we can observe right here, is the same as the one that we did observe. And then when you giving me a little circle, and it's not. Okay. Well, I'm going to keep on talking while PowerPoint thinks at me. But as you know, then you're going to say, all right, well, if I want to figure out what the counterfactual mean that I need in the post period to calculate that average treatment effect is, I'm going to start from the pre-period. There we go. Start from the pre-period for the treatment unit. Okay, so that's that piece. I'm going to add to it the change that I really did observe for the controls. That's that piece. And then that's going to tell me what the counterfactual that I need would have been. And this is like how you construct this simple 2x2 differential, of course, right? So that's just tell me that, this is log spending. So it suggests this differential analysis with these four dots says that this program, if you believe parallel trends, caused spending on these operations to fall by 2.3%. So that's great. That's a simple world. That's like two slides of simple 2x2 differential. However, that is not what the paper did. Paper dealt with a geographically staggered rollout of this policy. So in short, Humana needed like a third-party contractor to deal with this payment program, and they had to pay per state. And some states had a lot of practices that did this, and some states didn't. So they said, well, since it's a fixed cost per state, we're going to do it in the dense states first and get our money's worth. And if it worked, or if we want to see what else it did, we're going to roll down to other states after that. So some states got it in 2016. Physician practice adopted it. Some physician practices did it in 2017, some in 2018. So it's a staggered rollout, which I think should be familiar because many things in the world are staggered rollouts. And this is now we're moving on from, simple 2x2 differential that we've kind of known about more or less since the 1850s to this more complicated situation that feels differential-like, but that is the first one that I think this new literature has really started to dig into. So the first thing I want to ask, there's a sidebar, like I think the temporal ordering of research on this was to say, here's a staggered rollout. We typically analyze this with a regression. Is the regression good or bad? And that my work is about how that regression is not so great. I'm not going to tell it to you in that order. I'm going to say, here's a staggered rollout. What is a good way to analyze this? And then we'll circle around at the end if we have time and say, what would have gone wrong if we had done the regression strategy? So if we're going to go with this parameter first approach, we have to ask ourselves, well, what does ATT mean in this situation? It means something different. Because before there was just one treatment group, one post period, one average treatment effect on the treated parameter. Now there's a lot. So this is what their actual kind of aggregate data look like. This is a figure from their paper showing average spending by timing. I call them timing groups. Some people call them cohorts. So like, for example, you can see like the 2016 treatment group is here, and they're untreated when the line is dotted, and then they become treated here, and their spending falls. Here's the 2017 in orange, and then you can see how this is pretty much, figure is showing you almost everything you need to know to analyze this policy. So no internal Humana data required, really. This figure is all you need. So when you look at this, you should say, well, okay, there's actually going to be an ATT type parameter for each year of this line. I'm about to define for you like the same simple definition, but it's an ATT, but it's going to be specific to a timing group. So that's the 2016 switchers, the 2016 practices, and a time period. So these practices have an average treatment effect in the year 2016. They have a different treatment effect in the year 2017. They have another treatment effect in the year 2018. And that's true also for the 2017 group, also for the 2018. So to me, this is the most fundamental thing that you can take from how to think about these studies is you can go from saying, yeah, two group diff, very simple, I totally get it. And then the situation gets more complicated. And I want you to always think to understand how you can take this seemingly complicated situation and break it up in your mind at that parameter stage into similarly simple objects. There's just not a lot of them. Yeah.
Why? Is it because you have multiple comparison groups now, or because you have multiple treatments, or both?
Well, it's multiple treatments. We'll get to the comparison group question is a really interesting one.
Yeah.
What is the comparison group? It's actually a question about what parallel trends assumption do I believe. So that's question number 2. This is just, all we're saying now is just what kind of treatment effect parameters exist on this graph right now, like exist in this world. And we're not even talking about designs, we're just saying there's just many, what I started to call building block causal effects in this graph. Previously, there was just one, now there's many. So this is what they look like. And in fact, they look just like what I wrote down before because the notation seemed complicated at first, but now you see why it was complicated. Because an ATTGT, and this is like, that notation comes from a paper by Brian Calloway and Pedro Santana, which is my favorite one of the new kind of estimation approaches. But their approach to estimating is to start from defining these building block parameters, I think, in a rigorous way. So an ATTGT is just what we were saying in the previous figure. It's an average treatment effect on a treated parameter for a given timing group G. So G might be 2016, G might be 2017, might be 2018, and for one specific time period, just one time period at a time. So it's the average of a causal effect of being treated at time G. It's averaged. Okay, it doesn't have to be averaged, but we're talking about averages here because we chose to. And it's only averaged over the units that really were treated at time G. So this is like a really well-defined building block kind of causal parameter. It looks just like it's just like the 2x2 type parameter we were going after. It applies to one treatment group only, G, and in one post period only, time T. That's it. So with this in mind, we can proceed in thinking about what does parallel trends mean? Because spoiler, it's going to be kind of the same thing as it meant in the 2x2 case. What does our estimate mean? Well, we're going to estimate a bunch of these things and we'll average them. So we'll know what that means. And it's going to really clarify like all those choices in ways that we'll go through. But I just want to linger here and say, this is, I've said it a couple of times, I'm going to say it again. This is the most important kind of new step here to me, is getting this part straight in your mind. Because I think when I used to do these studies and approach and say, like, what kind of regression should I run? I didn't know what kind of causal effect I was after. And therefore, I didn't really know what comparisons my regression was making. I didn't really know what parallel trends assumption were required for those to be good or bad comparisons. But each of these little pieces is just going to be analyzed just like a 2x2 different diff. It's just that you're doing it a bunch of different times instead of just one time. And that's great, because I think then we're not telling you you need to do a new complicated thing. We're telling you you need to do a simple thing many times. And that's, to me, that's a lot easier. So at that ATTGT level, that's where we're going to talk about like identification and parallel trends. That's what you're going to estimate. Like that, you should think about just estimating each of those pieces one by one. And then you're going to have to combine them. And you see the pink is showing up again. You're going to have to think about how do you want to combine those things. You could average them or combine them in many different ways. So let's look at that just for a second, because we've now kind of split this whole analysis into like the parameter definition. We'll talk identification, parallel trends. That's like one other theoretical step. Estimating, that's just like taking the means and comparing them in a certain way. And then aggregating, because when you have lots, you have to average. So let's talk about the averaging. So let's look at this again and say, all right, on the left, we're just going to list like different treatment groups, treatment timing groups. If time is sort of on the x-axis, these are a set of different ATTGT parameters that exist in this study. I'm just showing them to you for 3 groups in 3 years, but there could be more. So think about these ones, for example. These are the instantaneous effects. 2016 effect for the 2016 group, the 2017 effect for the 2017 group, the 2018 effect for the 2018 group. So if you, for example, wanted to know like what happens when you do bundled payments, like what happens right away, you want to know those green numbers. There are second year effects too. You might want to know, well, maybe the physicians kind of don't know that the payments are different. Maybe it has to get communicated. Maybe there's a little bit of lag. So we might care about like what happens like a little bit later. Well, you can see that too, but notice you can't really see it for all the groups because these guys only are observed for the first year. So it's still there, but it's not there for every cohort. So this is immediately you should start thinking, it's going to change sort of the average groups to whom my estimates might apply. And then if you want to know like what longer run effects, you're going to know them for even fewer. And if you want to know like really long run effects in your data, you can only know that for the earliest treated units. And so there's this sort of trade-off between like how long you want to see the effects versus how many groups that they apply to. And that's just, again, that is not a thing that's baked into some analytical choice that you should make. That's a choice at the very front end of your study about like, what do I even want? You want long run effects, totally legit thing to want. You just need to recognize that you're going to only be able to do that for some of your treated observations. So then you can think about, all right, well, what if we want to average them up? Like it's not going to be practical in a study with many treatment groups to just show me like a million numbers or a bunch of different lines. I'll show that to you and then you'll see that it's very messy. So aggregating these things is a key step too, just for practical purposes. So again, that's going to relate to what we just talked to. All we're doing now is just realigning them up based on event time, like time since the treatment started. And you could just think about averaging these things, based on how big each group is, right? And then how many treated out of all the treated units in your data, how many are in group G? That's a reasonable aggregate. I mean, you could aggregate other ways if you wanted. You could weight them by population. You could do anything. Then again, you choose. But notice that when you go to the second year and you don't have this third one anymore, well, now the weights are kind of like changing. Imagine that these were 1/3, 1/3, 1/3. Now they're going to be half and half. And so this is, if you were to plot me the average of the average of 3 numbers in the first year and the average of 2 numbers in the second year, all of a sudden those first 2 get like way more weight than they did in the first year. But that, again, that's just a thing you should know and you can make choices about it. And then finally, like the last one is there's no weighting at all because you only observe it for 1. So this is just a little like schematic of how you should think about how you should think about breaking up these complex designs into simple little things. And then how it's not, the message I want to convey is it's not like a complex econometric statistics choice about how to navigate these things. It's simple-ish, but important to think through to keep yourself straight about like what numbers am I showing? Why do they change over time? What does each one mean? That's very, very attainable for everybody. And then of course you could also just average them all into a number if you wanted, that's fine. All right, so and I'm going to give you 2 examples of how your writing could actually reflect this precision that I'm advocating that you do. So suppose that you were doing this study and you wanted ATT0, the average of the immediate effect. I think a reasonable way to write your objective statement in your JAMA submission would be to estimate the average first-year treatment effect of this thing, at participating physician practices. To me, those words reflect that parameter very quickly. Suppose that you wanted the average of all those effects that I just showed you on the last slide. You could say you would like to estimate the average treatment effect of this stuff during patient episodes. Like I wrote it this way because the early treated units have 3 years. They have more episodes than the later treated units. So patient episodes at participating physicians. There's many ways to do this, but I want to emphasize again, like not only are we being precise in the definition of what we want mathematically, but to me, it also maps to like the language in a really important way. Okay, so we want some ATT, that's fine. What do we need to believe to get it? Well, we kind of already know. Like it's just each of those ATTs is like one parameter, one treatment group, one post period. It has the same kind of unobserved counterfactual component. We just need a strategy to figure out what would the untreated outcomes have been of the treated units had they instead not been treated. And we're going to use a parallel trends assumption to get it. It's just that now we need to define parallel trends slightly differently. So this part's kind of the same. Well, no, actually, sorry. The second part's kind of the same. This is what we want to know. What would have been the change in untreated outcomes for the treated groups? But this part's new. And the new part is G comp. That's like a little fancy G comp. This is where we get to the question about control groups, because with a staggered design, it's not obvious who you should compare to. When it was treated and untreated, you compare to the untreated. But now there's actually a lot of ways to define untreated. So let's talk about what this is going to look like, and then what we could choose for the comparison groups and what those choices might mean. So let's go back to this picture and say, all right, suppose that we wanted to know, we wanted to compare the 2016 group, that was our treatment group, and we wanted to compare it to 2020 group, right? Then that was just the controls that we happened to choose. And we wanted to get the treatment effect in the year 2017. Well, this is what we do. We compare, we take the change in outcomes of the 2020 practices between the years 2015 and 2017. That would be a change for our control group. That's what we think would have happened to the treatments had they instead been untreated. And so we would be saying, this is the counterfactual we think would have occurred. And that suggests that the treatment effect is going to be a difference there. But let's talk about what that control choice. Why did we compare to the 2020 group, and what does that mean? That's not the only thing we could have done. If you look at this picture, you can make many different comparison groups. G-comp can be a number of different things. So when you are trying to navigate, when you get to this point where you're saying, okay, I've got a staggered thing, and I've got to navigate this new literature, and there's like this Son and Abraham estimator, and there's Callaway Santana, and there's stack diff and diff, and there's the Shays Martin and Dafoe. There's all these things. Like, what am I supposed to do? Almost all of them differ in this choice. They're doing fundamentally the same thing. They're just choosing the control group slightly differently. And some of them give you an option to choose the control group slightly differently. So imagine that you had in your sample some units that never do the policy. And in the Humana example, their data go through 2019, I think. And so physicians that adopted the bundle payment policy in 2020 are essentially, they're never treated. I mean, they're treated in the future, but in the data, they're just not treated at all. So you could choose them as a comparison, that's fine. And that's going to be the same comparison group for every one of those parameters. You're just going to compare every timing group between every pair of periods, just always compare them to the untreated units. Yeah.
Maybe this is a dumb question, but is the idea that the choice of the comparison unit here shows up because you're not sure of selection to treatment?
Yeah.
An RCT means that all those would be the same.
Yeah, definitely, for sure. And there's really interesting papers about like how you should handle timing variation when the timing is randomized. There's like even trickier, like more efficient strategies to handle timing. Here we're assuming there's some kind of selection to treatment. But that, I think you're hitting on the right thing, which is this is not just a choice that's like kind of arbitrary. You just choose what you want. Each of these choices corresponds to a different parallel trends assumption, right? So I wrote it on this slide in this way because G-comp could be any of these groups, but whichever one you choose, that pins down what parallel trends you have to believe. So some people don't like choosing never treated units because they say, this is a super specialized program. It's for physician practices that see older people who need knee surgeries. Or who need knee replacements. We don't want to compare them to like OBGYNs. That doesn't make any sense. So OBGYNs don't get this bundled policy, but they might. Why it doesn't even make sense to compare to them as controls. So some people say this is not a good control unit and you want to choose something different. Instead, you might want to do something like this. And this is what JAMA paper does. Compare to other units that are treated. They're just treated at a future time. So that would be like saying, we don't even want to just compare to physician practices that do outpatient, knee replacements. We want to compare to physician practices that do outpatient knee replacements and chose to do the bundle policy They just didn't choose it today, they chose it 2 years from now. And that's good, that really, really pins your identification down to variation in timing. I did it today, so I'm the treatment group, and you did it 2 years from now, so you're the control group. And that's good, but notice that it's gonna make it hard and impossible, in fact, to estimate any effects for the last treated unit, because if you're last, there's no one ahead, so you have no future treated control group. That's fine, but it feeds back to the parameter stage. Now your parameter applies to all the treatment cohorts except for the last one. You could combine the two if you want. Sometimes you think both are parallel trend is going to be satisfied for both, in which case you can combine them and you get more control units and more power. That's good. And then sometimes, you can pick anything in between here. So if you're looking at this literature and you read Son and Abraham's really nice paper, they propose an estimator that just always uses the last cohort as the control. And you could do that too. So I'm not even saying these are the only choices you could make. These are just the most obvious ones. But the pink is showing up again. This is the thing that you choose. And you choose it based on what you know from outside of statistics about how your program worked. Why did it go into place in some place versus another? Like, what's plausible? And this is another thing that I love about, I think, this new literature is that it's by being clear on these steps, it makes it much clearer where your non-econometric, your non-statistical knowledge is really important in the process. Like, econometricians cannot tell you which of these things are plausible or not plausible, but you can, because you have all this like context expertise. A couple of notes on what it means to be willing to believe parallel trends in this case. I kind of mentioned this just now, but you need to know something about why is this varying. So again, that's like outside of the econometric context. It matters for the econometrics, but it doesn't come from the econometrics. One of the advantages of diff and diff in some sense is that it allows selection on levels. Like, it's okay if in the pre-period your treatment and control groups are far away. But that's not totally free. It's not always true, because there's lots of things that means that the transformation of your outcome variable can really matter. Like, parallel trends in general is not going to hold in levels and in logs, unless the groups are like right on top of each other. There's a really nice paper by John Roth and Pedro Santana about that. And this also kind of relates to like bounded outcomes and nonlinear models. I mean, if your treatment group starts off at 0.8 as like 80% as a rate, but your control group changes from 0.3 to 0.6, it's not possible for your treatment group to have changed by 0.3 units because it can't go above 1. So that is a feature of the outcome variable that does allow some econometrics to tell you that certain control groups are not plausible. And it just gets you into nonlinear models about this. And then finally, parallel trends in general need not be plausible. Parallel trends is another way people say it is bias stability. It's just saying like the bias I observed yesterday, the gap between my treatment and control groups, I assume that's exactly the same bias as today because I'm fully just subtracting it off. But there's lots of sort of time series properties that could suggest that's not true. Like, what if things were kind of mean reverting to some sense and units were off by 1? If your groups were off by 1 yesterday, maybe what you actually think is that they're going to be off by more like 0.9 today because maybe those gaps are shrinking over time. In which case you don't want to do different. That's not parallel trends. That's something different. And you could condition on past outcomes in a regression framework if you want. And there's a really, really nice paper by Ding and Lee that talks about the difference between a lag dependent variable estimation approach and like what assumptions is that based on compared to a different estimation approach based on parallel trends. And I think it's a great paper because it actually shows like how the two numbers you would get from doing those can, under some assumptions, fall on either side of the true effect. So if you do both and they're pretty close, you're like pretty sure that the number is falling in this range. Okay, so what should you actually do? Well, we decided that we wanted an ATT. Suppose we decided about the control group for which we believe parallel trends. Well, then it's pretty clear what to do. We're back at, because we broke the parameters up into simple pieces, we broke the estimation up into simple 2x2 different diffs, just a lot of them. And so again, it's just going to be mean. This is just a compact-ish way to write the change in average outcomes for the treatment group. Notice also too, though, that it's all this is pegged to what I'm calling G-1. So there's other ways to do this, but all of these analyses are using the year before treatment as the omitted period. So it's going to be like G versus G-1, that's the year 0 effect. G+1 minus G-1, that's the year 1 effect. It's all going to be pegged to that. But it's none of this is just a slide saying if you define the parameters this way, you get to do a bunch of simple different ifs. So this is something I talked, same thing I said 35 minutes ago. So we can look at this, let's take this, let's log it, because they do this thing in logs. If you wanted to get the ATT for the 2016 group in the year 2017, right? So notice over here, like we're going to use this ATT GT notation. This is the parameter we want. Suppose that we want to use as controls the average of everybody not treated yet. That's going to be the average of those lines, those lines up there. We're going to get the change that we see for the average of those dotted lines. We're going to apply it there, and we're going to get a number. And we say, okay, well, the ATT 2016 group in the year 2017 is a 4.1% reduction in costs. It's freezing up on me again, but we can, the next slide is just showing you that if you wanted to do, oh, there we go. Okay, so now you want a different parameter. You want the ATT for the 2016 group, just now in the year 2018, just do it again, just with a different gap. And you can think about estimation proceeding by just doing this for every combination that you want. And you don't know, there's no regressions in here. I mean, you can do it with regressions if you want, but it's all just averaging. And if you do Callaway and Santana's command, like it is doing this. It's just going through and subsetting the data based on the control group you told it to use and just calculating like all these numbers. And when you run that command, the output you get is a huge like list of numbers of every ATT GT that it estimated. And here I estimated them by hand and plotted them. So right now, this is what you would get if you said, my analysis is going to target all the ATT GTs. I don't want to aggregate it all. I want to estimate all of them and show them to you. You could do it, but you're going to get a kind of messy looking picture like this. But you can see it looks pretty good. This is just data I pulled from the figure of their paper. Like this is nothing with their microdata at all. You can see that, the first year effect for 2019 seems kind of weak, but like everybody's going down afterwards. Looks pretty good. You can line them up by event time. That's a little clearer. And you can see, yeah, these are noisy, but of course they're noisy. We're slicing the data really thin for each piece. So that's another consideration when you're thinking about aggregation. This was a very clear discussion. This is a very clear way in my mind to think about like identification of each piece and interpretation. But of course, in your real data, I'm asking you to use a very few number of observations to get each dot. So it's not surprising that they're noisy. Another good reason to aggregate. So this is a way to present all the parameters, but you could also just average them, in which case you get this pretty great looking event study right off of their figure. I just average those numbers equally. This is actually a place where you can see how averaging really matter, because I don't know the size from their paper. I don't know the size of each treatment group, but actually look at this. I mean, if the 2016 group was very big, they got way more weight, then the first year or the year zero effect would get dragged up towards zero. Right now, I'm giving it equal weight. And so the first year effect is kind of negative-ish. But this is the heterogeneity is another reason why you need to think super carefully about the aggregation step. It matters, like how you're going to average these things. And in the regression world, we were just letting regressions do that for us when we really should, I think, thinking clearly about how to think about it. Okay, so that's like there were no covariates here. This was just like the logic of how to take a complicated design, break it up into simple kind of building block parameters that I think are easier to understand than something overarching. Feed that through a parallel trends kind of thought process, like what's plausible, what's not plausible. Use that to guide your estimation, and then aggregate parameters at the end, and you get something pretty great. There's a lot of other things you might want to do. And I'm going to just appeal to these set of blueprint questions and say, well, what if you wanted to believe something different? I define parallel trends in two periods, G-1 and T. But if you thought that parallel trends was actually true relative to every period, so not just G-1, but if you thought it also held relative to G-2 and G-3 and G-4, you can use that stronger assumption to buy a little bit more. And I'm not going to say a ton about it, but in the space of estimators, Orusiak, Jaravel, and Spice and Wooldridge have what they call like imputation estimators. And this is a place where I think there's a ton of confusion, including some in my own mind. But basically, these are different ways to handle the data, but they're not just arbitrarily different. They're different ways to estimate, and they come from making a slightly stronger parallel trends assumption. So if you dive into papers like this and you say, I don't know, should I do Callaway and Santana or should I do imputation? It's a legit question. you can do imputation if you believe something stronger, and you might get a little efficiency out of it. But, in some ways, it's not doing a whole lot very different. And so I think clarifying like how this approach differs from what I just walked through is helpful. But I'm gonna just tell you that that's a sidebar you can go down right now if you wanted to. Okay, so what if you get to the end and you say, well, I don't know. I mean, I made all these parallel trends assumptions, but they don't seem very plausible. What should you do? Okay, well, if parallel trends wasn't plausible, you need something new that is plausible. Otherwise, you don't have a causal study. So what can you do? Well, one thing, this is where covariates can help. So suppose that you said, suppose that the income distribution of patients at different practices was really different. In the early group, had they served a bunch of wealthy Medicare recipients who were super active and had easy recoveries, no complications. And then other practices were different. But what if it were true that parallel trends did hold between rich patients and poor patients, but the composition is just different? Conditional parallel trends just says, okay, we'll make a different assumption. We'll assume parallel trends for one type of patient, and then we'll assume parallel trends for another type of patient, and then we're going to fix up the comparisons so that we are essentially comparing doing what we just said, but only for a certain type of patient, and then doing it again only for another type of patient. That's a different assumption that's weaker. The way to implement it gets into a lot of statistical techniques that, again, I'm not going to talk about. Santana and Zhao, though, discuss how you can use reweighting by the propensity score to achieve that. You can use kind of modeling of the outcome as a function of say patient income to achieve that. Or if you want a doubly robust estimator, you can do both. So this is another sidebar, what's the proper way to include covariates in a diff analysis? What I want to highlight is that it comes from saying, well, regular parallel trends wasn't that plausible. Let's go back to step number 2 and make a weaker assumption and then see how that flows down to our estimation approaches. And then another way to deal with this is to say, okay, well, maybe I don't have covariates that are going to fix this up, but I'd rather than saying parallel trends exactly holds, which if we look deep within ourselves, we all know it doesn't exactly. It's close enough, and I think we want to get as close as we can, but it's never exact. You can just say, okay, but what if I do something weaker in a different way and say, what if it doesn't fail too badly? And I'm willing to say what too badly means. Then you can bound your estimates, and you can use these really nice methods in Rambachan and Roth's paper to get a confidence interval around a set of identified estimates. So you're I don't know that the ATT is negative 2.3, but I'm pretty sure that it's between -3 and -1.5. And Ramachan and Roth's sort of magical econometrics approach here is to say, here's a confidence interval around that set that you can get. And so then you can make statements like, even if parallel trends are violated to X degree, I can still reject the null hypothesis that this bundled payment program doesn't do anything. And that's I love when I've been able to make that statement. So I am at a point where I can do 2 things. I can either talk briefly about how regressions could go wrong, or I can take questions. And I'm happy to do either of those things. Does anybody have a preference about just open up to questions, or dive into I went through the process I think is good, and I can highlight how you would have gone wrong if you had done the regression thing.
I kind of like both.
Okay.
Does anyone want to do a quick question now, and then we can move on to that? Yeah,
Completely ignorant of all that you said, except you did it so well that I almost think I got.
Good. Okay. Good. No, you did. It's very graphical.
It is. So, okay, I'm sitting here going, first of all, I can imagine there are journal editors that have very preconceived notions about superiority of one approach versus another.
Yeah.
So then when you're actually submitting this, do you have to essentially do it all the ways?
Oh,
And
yeah.
then say, we like this one the best, but also we do these other ones, and guess what? It wasn't different. Or is it that just way too much work, and plus your data can't really do all
No,
the
I have
ways?
thoughts about this. I think one concern is that people do it all the ways, and then we all have to read really messy, annoying graphs where the things are not that different. That's just visually offensive. Then there's the kind of do it all the ways approach, but without any kind of like interest, any kind of meaningful discussion of why did you do it all the way?
Yeah.
So that's why to me, it's really important to understand this like choice comparison group, because you can't just say like, I did it all the ways. Why though? You know, like, I mean, if you think that they're all fine, then just do one way that's like the most efficient, given that they're all fine. But if you don't think they're all fine, why did you do it all the ways? And then I've heard a journal editor tell me there's this other concern, which is I secretly did it all the ways, but I reported to you the one that I like the best. And then that's like a new kind of pre-test type of bias. So I think we don't know how that's going to play out right now. So my goal, the big place where I got from this, and then my goal is to say, we should just understand why they're different. And that to me, it's all step 2, right? It's like, it's what are you willing to believe? And if you can understand how the ways are based on different assumptions, then we can move this entire discussion to assumption land and say, like, let's talk about which of those assumptions is more or less plausible. And you know, then you can, if you say they're all plausible, great. Now we can move on to some efficiency discussion. If they're not all plausible, well, your decision's made for you. I used to be deeply confused about this, and I probably would have defaulted to like, I don't know, I tried it all. I think I have a better understanding and hopefully can convey it about how we can address that exact question, but like in a more, I think in a more substantive way. Right?
I feel like I'm kind of in the same boat where I think I understand everything, but now I have more questions. So when you had that graph where you had the x-axis, the negative positives, are you saying with a staggered time difference, we should just center the data so
Yeah,
that
that's a
everybody
really
has
good
the same
question.
time?
Okay, that's a great question, because when we were all thinking about how to specify our regressions, it was confusing what to do here. I think what I'm saying is when you have a staggered timing, you could graph it like this, and there's no centering. It's just t. That's it, just year. And that everybody knows what year means. But it's just a choice. And but so maybe I should say this way. Here, there's just year. Well, we already did all our estimation. We estimated everything. There's no more estimating to be done. It's all on this graph. Then it's just a choice if you would like to center them and plot them like this. It's just a plotting choice. And then if you want to average them, if you would like to average them, you'd like to average the numbers that fall at event time 0. That is an aggregation choice, but you don't have to do that if you don't want to. You could say, let's average the treatment effects for treated units in time 2016. That's an average you could take. That's fine. Then you could just choose to do that. And you could just choose to aggregate the 3 treatment effects that can be observed in the year 2017. So these are all, this is a great question, because it drives right at the heart of the difference between estimation, which is getting all those dots, and aggregation, which is just what's a good way to summarize all these dots. And so it's like, it's totally in your hands what to do. It's not, neither is right or wrong. It's all about like, what do you want to report? And a typical thing is to report an event study where it is aggregated, but this does not have to be the picture that you report. You can choose to report different averages, different pictures. Like,
So this might challenge your skills as a communicator. We have 3 minutes left, but I'd like you to say a few words about what OLS was doing without our permission,
Yeah.
because I was not aware of that
Yeah.
until you started talking about it. And
Yeah.
I think it would be good for people to hear.
okay, all right, I can do it. So let me just start off by saying, what did we do before? Well, we didn't really think about this set of questions before. We just said, let's do a fixed effects regression. And I think I have a good idea why we liked to run a regression of outcomes on unit fixed effects and time fixed effects, and then just a dummy for like when the treatment turned on. I think I know why we liked that. Because when we had a 2x2 data, like, we were able to regress Y on a treatment dummy and a post dummy and the interaction of treatment times post. And when things got more complicated, we said, well, I mean, that regression doesn't work anymore, because now treat means a lot of things and post means many different things. But I think our sort of like ingrained regression logic was like, but I can do better though. I'm going to put in unit effects, and that's like more general than just post. So it's more general, so it has to be better.
Is it the same when you only have one time period?
When you just have two time periods, this is exactly the same.
Yeah,
as
okay,
regression.
yeah, thanks.
Exactly, yeah. So yeah, with two time periods, regression estimation is no big deal because the regression is just an averaging machine.
Yeah, right, okay.
And then we said, okay, but I can't, it's hard to get the regression to work, so I'm gonna be more flexible and put in unit dummies. That's gotta be better. And I'm gonna be more flexible in post, and I'm gonna put in all the time dummies. Like, it must be better, right? It has to be. And then we said, okay, and then we were a little coy and unclear about like what the coefficient here was. So my actual work in this area is to have had the willingness and like the pain tolerance to just do a bunch of algebra on this regression coefficient, figure out like what is beta hat in terms of means. Like, I just only understand means, and so I just wanted to break that thing down in terms of averages of y and figure out what it means. And I'll tell you that in a 3-group example. So it's just me doing algebra using about how regression coefficients work. Imagine that you had this is the situation I like to use to describe it. Imagine that you had a very kind of simple staggered timing. So we're not on mean replacements anymore. It's just data I made up. There's like an early group, they get treated at time k, and they're in the triangles. There's a late group, they get treated at time L, that's a little L right there. They're in the open circles, and then there's untreated group, they're in the gray. Suppose this is the data that you had. The way that I started thinking about this is like, well, actually the challenge here is there's kind of like too much information on this graph. If you had less information, it would be super clear what to do. So suppose that you did not know anything about the later treated units. They weren't even there. You would know just what to do. You would calculate a diff and diff. You could, if you wanted, calculate a diff and diff that compared the post period, all time periods after K, to all time periods before K. You compare the triangles to the gray, and you would have so call this little number right here, beta hat, K, U, because you're comparing A to the untreated units. If instead you had no information on the early treated unit, you would be in a similarly simple situation. You'd say, oh, I have a simple diff and diff. I compare the circles to the gray after time L and before time L. And these are all, you'd be very happy and nothing would be confusing. And even if you only had if you had the two timing groups, but your data just stopped short of L, you would also be happy because you would say, oh, no problem. I don't even care if the circles got treated later. I'm going to compare this little middle window to the pre and the middle window to the pre for the triangles versus the circles. The really tricky thing that regressions do that maybe wouldn't have crossed your mind, but like technically it could possibly work, is that regressions will incorporate this as well. They'd say, all right, I have no information on the pre-period for those triangles. But even though they're treated all the way through. So I'm gonna use them like a control. Yeah, they're already treated, but their treatment status isn't like turning on or off. They're just all the way one. So I'm gonna compare the people who enter treatment to the people who already have been in treatment. And that's functionally kind of like a simple, I mean, it is a simple diff and diff. It's just using this already treated control group. And so I look at this picture and I'm like, I can pull out each of these simple comparisons. And it turns out that's just what the regression is doing. So the result of my work here is to show algebraically that beta hat diff and diff from that regression is an average of each of those 4 things, right? So each of the betas of this regression is one of those pictures that we just looked at. One simple thing comparing a group that enters treatment to a group that does not enter treatment, meaning might be untreated, but it might be always treated. It just doesn't enter. And the weights, so that's fine. We can talk about what that means. Those are the components. So this should actually look weirdly like what we just talked about, because I'm telling you that an aggregate estimate, beta hat diff and diff, is an aggregation of simple estimates. I just pitched you a whole hour on why that's good in another way, but I'm going to tell you why this particular version is bad for 2 reasons. One of them relates to these weights. The weights in this regression are a little bizarre. I mean, as all the discussion we just had about aggregation, this is what regression is doing under the hood. It's taking the sample size that's in each of those little 2-group samples and squaring it. That's part of the weight. So that's fine. Bigger subsamples get more weight. That's okay. But it's also weighting by a measure of the variance of treatment, like in that sample. So if treatment is a dummy, its variance is highest when it turns on right in the middle. So units that are treated in the middle of your panel get like a lot more weight than they should get, and units treated towards the end don't get enough weight. And then, I mean, that's just what regressions do. They're minimizing variance. And so if some unit turns on only in the very last period, it's mostly a control. So its treatment effect doesn't get that much weight, and that's the variance part. And if a unit turns on really, really early, kind of the same thing happens. So the weights are, I'm just gonna argue, just assert here that the weights are weird. Probably nobody would have said at the outset of their study at the parameter definition stage. I would very much like a weirdly variance weighted average of these treatment effects. But that is what OLS is giving you. The really concerning thing is what happens when treatment effects change over time. So let's imagine, this is the last thing I'll say on this. Imagine that you had a thing where the early group turned on it at T star K, and its treatment effect was not a shift, it was a big trend break. So treatment makes outcomes start to grow faster. And then a little while later, the black line becomes treated and they get the same trend break. Well, this is a simplified version with no control group. So it's going to average one diff and diff that just uses those periods, compares the gray to the black line in this middle window and the pre. That's fine. That's going to give you a number that's sort of like the average difference here between the gray and the black, and it's a positive number, positive treatment effect. That's fine. There's a second diff and diff though that compares what happens when the black line enters treatment to the gray. That one is not fine because in words, the gray line is on a differential trend because of the treatment effects. So if we're saying, oh, what would have happened to the black line if it had instead not been treated? If we use the gray to make a guess about that, the gray line is growing like crazy, but not because things are growing very fast in an untreated world. It's growing because the treatment effects are growing. And so by baking in this comparison of a late treated unit to an already treated comparison group, the regression is going to get this one totally wrong. And in fact, in this example, the little 2x2 diff and diff you get by comparing the change in the black line to the change in the gray line is actually a negative number, even though these treatment effects are obviously positive. And that's the sense in which you can get regression coefficients that are not even the right sign. They can go the opposite direction. So I can actually show that to you. Fine, I'll end here. If you go back to the example that we went through with the knee replacements, the black line is the nice average that we constructed, and we were very rigorous about it. And it tells us that spending falls by 2.7%. The gray line is two-way fixed effects. And you could run that event study and say, oh, this is great. It's a really good looking event study. What we know from how these are constructed, though, is that you might think that gray looks better, but it doesn't matter that it looks better. That's not the criteria we want to use. It's like a weird average kind of number that you should never have wanted. So just because you can fiddle with your data to make a line look flat doesn't mean the line is really flat. And two, if you wanted to summarize this gray line with a diff and diff coefficient, you're going to get an average of negative 1.5. That's like almost half too small. And it doesn't even make sense because the gray line is lower than the black line, and yet its summary measure is too small. So that's the time varying treatment effect, not a bias, just like striking and showing you that your regression is giving you a screwed up answer. Whereas if you went through in an orderly way, you know exactly what every dot on that black line means. And I think the same cannot really be said of the gray thing. So anyway, I think going through these questions is an orderly way to organize both your choices and your interpretation. But if you just sort of jump to the middle of it and check things later, you're gonna either be disappointed or confused, and it'll not only be wrong, it'll probably waste a bunch of your time. So thank you.
Well, thank you so much, Megan. That was great. If you are a doctoral student, or you used to be a doctoral student, or you are Andy Fenelon, you are invited to hang out with Bacon for a little bit. They're going to be setting up a lunch in this room, so we should slowly move the conversation over to the commons. And see you next time, everyone.